Thank you very much for watching. I'm Arno, and I'm going to tell you about the C++ rvalue lifetime disaster. Unfortunately, my French is not quite good enough to hold talks in French, so it's going to be English. Yes, this is something that we actually encountered in our development, the trouble with rvalues, and I want to tell you a little bit about it. So what are we going to talk about? We are going to talk about rvalues and rvalue references. Now, first of all, where do they come from? The standard library advocates value semantics. So whenever you are changing something that's a value, then you know it doesn't affect anything else. And when you copy it, you get a real copy. And that's very easy to reason about. And so it's very nice theoretically. Unfortunately, that's a great idea, but in C++ 0.3, that's almost 20 years ago, it led to frequent copying of values because if you had these containers that were values and you copied them, then all the things that are contained in these containers, all these elements that are in a vector, for example, they got copied. And of course, that was very unsatisfying. So what did people do? They said, well, why can't we steal resources from things that you don't need anymore? So you really want to copy one variable into another, but you don't need the original, so you can just steal the resources, you reuse the memory and so on. And so this whole copying gets replaced by moving, which is nice. So here's an example. If you have a vector of vectors, for example, and you place back another vector into this vector of vectors of ints, then you would avoid the copy by saying, okay, I write a std move around my vec. I know that I don't need it anymore, and now I can steal its resources, and the memory gets reused for the vector that's inside the vector of vectors. Now that's all good for efficiency, but people saw that they can also use these rvalues for managing lifetime. Whether something is an rvalue or not actually tells you something about the lifetime of the object. If something is an rvalue, it's probably not alive for a very long time. So you better squirrel it away, or you're not going to reference it at least, so that you don't end up with the dangling references. In C++ 11, that was already done by std cref. So you could only pass lvalues to std cref so that you have sufficient lifetime for a proper reference. In C++ 20, it's also extensively actually used for ranges. The problem here is that if you have a range or a container like a vector, and you put an adapter onto that container, so an adapter like a lazy view, which will do its action when you are iterating over the elements, these adapters are actually referencing the underlying container. And if that underlying container goes out of scope, then you have a dangling reference, which is, of course, not terribly desirable. Actually, I should point out, there is a question and answer in Zoom. So if you have any questions, ask them there, and I will glance over at this window repeatedly so that I hopefully catch your question and can answer it while I'm going. Now, so that's undesirable. You don't want to have any dangling references. So what they did is say, okay, if you pass an rvalue to the construction of such an adapter, this is not going to compile. I'm going to assume that this rvalue is going to soon go out of scope, and then it's probably wise not to compile. Now, we were also using this rvalueness for lifetime decisions in our code. We have our own range library where we made the decision not to compile, but to actually aggregate rvalues into adapters. It's on GitHub, things are ranges if you want to take a look. And there we make a decision whether to aggregate the underlying container or not based on the rvalueness. So having correct rvalue or not is kind of important for what is actually happening. Before we go into these details, let's look at some of the rvalue usages for moving and the pitfalls that come along with it. Now, you have something like this here, like a function foo, and it declares a constant a, and then you return it with a std move. Now, what happens? Well, as you probably know, not a whole lot, because you still get a copy of that A, because you cannot move out of const. Non-const rvalues you cannot move out of. So this is probably not going to work. So let's leave out the const, so we'd have a better chance of getting a move. In this case, we actually do get a move. But this is actually not the best we can do. There is actually something called the named return value optimization, where essentially the variable that you declare in your function is already the place in memory where the return value goes. So the return value can actually be constructed right in its right place where it will eventually go. So and in order for the compiler to do that, you have to return a single variable, and this single variable also cannot be wrapped into an expression like a std move. So the std move would in this case actually makes things worse. The best you can do is you write it like shown here. You declare the variable non-const and return a, and then that return the variable. Well, actually, if you declare the variable const, you still get named return value optimization. So the move and copy is still elided, even if you then outside of the variable of that function, you keep using the variable non-const, which is kind of confusing, but that's how it is. Now, if you do the same in two branches of an if statement, then it's actually different, because the named return value optimization is only going to kick in if you are always returning a single variable. If the whole function, if the function is only returning a single variable all the time. If you return two different instances, and if you declare the same variable in two different branches, that's two declarations, that's two variables, then named return value optimization is not going to kick in anymore, and then you don't get your copy back. Because you declared things const. Now, since this is very easy to change and very easy to break, so if you wrote it intentionally, like with that const, with a named return value optimization, and afterwards you added in a branch in the if, and then suddenly you fall back to copy, I would recommend to always, when you want to move things out of a function, to always declare them non-const. Now, you can, in this case, improve it just by taking the const away. And then you do get the move. You still don't get the named return value optimization. Oh, here's another one. So let's say you have a member in a struct, and you construct the struct, and then you return only a member of that struct. What happens? You would think, well, it's pretty clear here to the compiler that you don't need that struct anymore. The B is going out of scope. So b.ma is pretty clearly there. It's pretty clear that this would be possible to scavenge the memory of this MA, to reuse the resources, so to move out of the MA. Well, it doesn't quite work that way. So these members of structures, even in a return statement, are not automatically rvalues. What you can do is you can write the std move around the B, the struct, and then actually the members are rvalues. This is all takes a bit getting used to, is a bit weird, but that's what we have from C++. So here are my recommendations. Again, make return variables non-const, and there is a warning in Clang -w move, which warns if you if you made any pessimizing mistakes with moving. So if you, for example, wrote return std move. Okay, here's another aspect of rvalues and their idiosyncrasies. You have let's say you have a structure B again, that inside has an A, and you have an accessor to that MA that returns by reference. Now, if you want, you can now instantiate a B structure and then get that A out of that structure with the accessor and assign it to a reference. So far, so good. It returns by const reference. And again, our variable is also declared const reference. So all is fine. Now, let's say we have a structure C, and that also has an accessor get A, but in that case, the accessor returns by value. And we want to use these two structures in generic code interchangeably. So we want to have either a B or a C, and then call get A on it. Now, the question is, what do we assign that result to? And it turns out that if you assign it to a constant reference, that's actually fine in C++, because of something called temporary lifetime extension. This whole concept predates C++ 11, so that has been around for a long time. And the idea was kind of, okay, you can always write auto-const-ref, and automatically the right thing will just happen. And the way this works is that if the get A returns by value, then the lifetime of the get A the lifetime of the variable that's returned, the A, gets extended. It doesn't go out of scope immediately, but only when your reference goes out of scope, the auto-const-ref that you assign the A to. It's a bit magic and a bit unusual for C++ to kind of do stuff behind your back, but that's how it is. So let's see how this works in combination of the double const-ref there. Which double const-ref? I've got a question. What's the meaning of the double const-ref? I don't see the double const-ref. Oh, B get A. B. Oh, that's just you can write the method here. I think I can mark it on the screen right there. This is semantically the same as a simple const. It basically says your this is a const ref. So it's the same as if without the reference. If you've never seen it, it's semantically the same. The idea is that you can now decorate methods in C++ with the way you want to take the this. So it can be a const ref, or it can be a ref, so an lvalue reference, and then it will not work for rvalue references. Or it can be an rvalue reference, like an ampersand, and in that case, it will only work for rvalue references. It's kind of the newfangled way to decorate your functions, or your methods beyond nothing or const. So it's a bit more detailed. The const ref, and I'll get to that. The const ref does nothing but what the const wouldn't do. It does make a difference if you have nothing. Then it means it either takes lvalues or rvalue references, both mutable, or you can specify it's either lvalue reference or rvalue reference. So in our code, everything is decorated either with const ref or with ref. We never have it undecorated because we want to kind of know when we use things with R values, precisely because of this lifetime problem. So either ref or const ref would be my recommendation. Okay, let's see how this works together with other parts of code. Say you have an operator less that's taking two objects, a const ref, and calculates some sort of less relationship between them. And we want to use it to have the minimum of two values out of std min. And in this case, what we are plugging in is the structure C accessor, which returns by value. So we have two values, and we calculate the minimum of them. Now we assign this to an lvalue reference, very much similar to what we did here, where we directly had auto-const-ref being assigned from the getA accessor. Here we just, push it through the minimum first. Now, that's how the minimum is implemented. And you can already see that we are probably in trouble because the minimum will turn the values getA into lvalue references, constant references, and return an lvalue constant reference. So the std min kind of already forgets about the rvalueness. And if we then assign that to our lvalue reference, the temporary lifetime extension is no longer invoked. It doesn't work anymore because the compiler doesn't know that this is actually a value. The only thing it sees is a constant reference. So that's where kind of the trouble starts. Now let's see whether we can get this a little bit better. We could say, well, I mean, the minimum is kind of implemented in a silly way because it takes constant reference. Wouldn't it be better? It would be forwarding. So it takes a universal reference and then it compares the two universal references and then forwards either the right-hand or the left-hand side. And let's say that left-hand and right-hand side have the same type here, which in this example they do. There are some extra complexities if they don't, but we'll leave them out for now. In this case, the minimum will actually return an rvalue reference. Now, the problem is that's all fine and good, but the temporary lifetime extension doesn't keep rvalue references alive. There is a difference whether you're returning a value, there the lifetime extension works, or whether you are returning an rvalue reference. And there, basically the compiler would need to actually create an extra copy for you because there's nothing to keep alive. It's just a reference. It's just a pointer at the end. And it can't be really kept alive. And the things where the pointer comes from, they don't really know that they got a pointer or a reference got taken to them, and they will go out of scope. The left-hand side, the right-hand side, they will go out of scope, and then you will have a dangling reference. Okay, that's problem number one. Now let's see. Here's another problem. Say you have a function that generates some a, and it's either a some function that returns a value or a reference. And for a function that is wrapping this factory function for a, this wrapper doesn't really care whether the factory or this generating function returns you a reference or returns you a value. It simply wants to pass through both these things. So it's supposed to return a value if some a generates a value, if foo is supposed to return a reference when some a returns a reference. Now, how do we do this? Well, if we do it straight away, if you just return whatever some a returns, we can do it with deckel type auto. Now, if we do the forwarding return with some code in between, it does get a bit harder. So you have here the question is the question marks. What should go there? And none of these things work really nicely. So if you do an auto-const, you can hope for temporary lifetime extension and say, oh well, I get a temporary lifetime extension. So it's if I'm getting a value, and if I'm getting a reference, then I'm getting a reference. So that's kind of what I want. But if I return it, then in this returning, the temporary lifetime extension is still a reference. It's still a lvalue reference. So foo is going to return an lvalue reference, and the temporary lifetime extension is going to expire. It's going to go out of scope, and you have a dangling reference. So that doesn't work. Now, if you return auto instead of deckel type auto, the whole thing works, but only if you at the cost of copying a. So auto-const a would still be either a lifetime extended reference or it would be an actual reference. But as soon as you return it from foo, then the auto foo would turn it into a value. So you'd always get a copy. That's also not what we want. So the problem here is with that temporary lifetime extension is that essentially it lies about its type. Really, it is a value, but that is only moonlighting as a constant reference, and that's not really practical because you may have other parts of the code that is reasoning about the type of variable that you have there in your hands, whether it's a value or whether it's a reference, and this temporary lifetime extension is just lying to you. So my opinion is this temporary lifetime extension deserves to get deprecated. It does the wrong thing as soon as rvalues come into play. Now, ideally, what we want to do in this case is we automatically declare a variable either as a regular variable, auto, if constructed from a value or an rvalue reference, keep in mind, also from an rvalue reference, there you also want to have a value because the rvalue reference indicates short lifetime. It goes out of scope, so you want to copy this thing. But if it's an lvalue reference, you can just take it by reference. And this kind of special way of declaring a variable proved to be very valuable, very useful. And we use it all over our code. Here's an implementation. Unfortunately, it only works as a macro. So we have this little Auto-cref macro. And it basically does what I said. It just turns anything that looks like an rvalue reference, or a PR value, an actual value. It turns that into a value, and lvalues, it just leaves alone. And this is how the implementation looks like. Now, if you do that, then it actually works nicely. So you have, you can use Auto-cref, and then the A actually either is really a value or an R value. And then you can return it, and the return will get the right type. And if you then declare this thing a decal type auto, it will return either a reference or a value. Keep in mind, no parentheses here. Otherwise, that type deduction will deduce the expression type, and the expression type of the A in parentheses will again be a reference, and then you get the wrong thing. I recommend doing this Auto-cref, making this Auto-cref basically your default auto. For us, it works very well. We have it all over in our code base. It doesn't work yet if the expression contains a lambda about basically using decal type in an unevaluated context. This has been fixed in C++20, but in this case, actually, the Microsoft compiler can do it, but the Clang compiler can't yet. Not even the latest trunk. So that's something that I'm still hoping for, that this will improve. And we are using the Microsoft compiler and Xcode side by side on the same code base. Now there's a choice. You could say, well, the Auto-cref conceptually really should be const, because, well, the auto-constref is const. So conceptually, if you're writing Auto-cref and you really don't care whether you're getting a reference, a const reference there, or you're getting a value, then that value should also really be const. So you're not writing code that works in some circumstances and it doesn't work in other circumstances. So in this case, you need, because of the return values that should not be const, you need some extra Auto-cref return if you want to use the Auto-cref for variables that you will later on return. Okay, now we combine all these tools. So we have an Auto-cref A, and then the our min C get A, C get A. And with our implementation, the forwarding implementation of min, and then everything works. So the our min correctly returns an rvalue reference, and Auto-cref then turns it into a value that you can then, happily do whatever you like with. Now let's look at another problem. So you have, again, two structs, and one contained in the other. And we are instantiating the structure B and then accessing MA inside that structure. Good thing is, in this case, the decal type of that expression is actually an rvalue reference. So the compiler knows that you've just generated an R value of B. And when you then access a member of B, then it will say, oh, okay, that's an R value. And then the Auto-cref will say, oh, that's great. Then we turn the A into a value. Now, let's put an accessor in there. So you have an accessor that gets the A by const reference. And I'm sure you've written these kind of accessors lots, right? Everywhere in your code, you have these accessors for accessing something as an lvalue reference, constant reference. Now, here, as I said, so first of all, this doesn't work. It doesn't work because, well, the result of your get A is still an A const reference. So this A that's here in the Auto-cref will still be a constant reference. it won't be a value. And then you get a dangling reference. That's bad. As I said originally already, you could write that with that additional ampersand here, hoping that this will eliminate cases where B is an R value. It does not, because R values bind to const reference. So it does semantically. There's no difference in between these two syntaxes. So this doesn't help you now. And there is the fundamental problem in C++ that a const ref binds to anything, including R values. And this will actually affect any accessor that is running on const ref, just like these here. I mean, basically, all constant accessors you have that you write are afflicted by that problem, that they probably won't work correctly if the structure is an R value. Okay, I call it R value amnesia. C++ kind of likes to forget about R valueness because you bind to a constant L value reference and then your R valueness is gone. Now, are the people who design C++ aware of this problem? Well, turns out kind of. Here's an interesting little fact. You have the ternary operator, the conditional operator. And you give that conditional operator two L value references, like up here, L and L, two L value references. Of course, then what you get back as an expression is of type, again, L value reference. Now, likewise, if you give it two R value references, unsurprisingly, you get back an R value reference. Okay, so far so good. Now, what happens if you give it an R value reference and an L value reference? Well, you would think, it's the R value reference can bind to a constant L value reference. That's fine. So it should be an L value reference, right? Or not? So I tried it out. Actually looked in the standard. It's actually an A const. So the C++ here forces a copy. It freely admits, I have no idea what's going out of scope here. I'm afraid, and I don't know what to do with this thing. So let's be safe and make a copy. And then as a value, you get actually a constant value, a copy of the references that you plugged in. Okay, so the conditional operator is afraid of R value amnesia. What about the common reference in C++20? It's a new trait that they introduced because in ranges, you have sometimes the situation where two ranges are kind of mixed together. You want to concatenate the range, or you want to merge the range, like two ordered ranges, put them into another ordered range, or form another ordered range from two ordered ranges. And for that purpose, you have two different kinds of iterators, and the iterator of the adapter that's combining these two ranges has to have a reference type. It has to return something. So you have two references that basically go in, and you want to represent these two references with a single other output value or reference, a single other output type. And there they had to face the same problem. So if you have two constant L values, then you get a const reference. If you have two constant R values, you got a constant R value. And indeed, if you get a constant R value and constant L value, you mix these two together, you get an L value. So even there, it just forgets about R valueness. All right. Well, out of curiosity, what do you get when you actually mix in a value? Do you also get a reference? No, in this case, you actually get a value. So why is that? I don't know. Now, I just know that common reference is happy about the R value amnesia. It just forgets about R values. So what's correct? what should we do? What's the problem? He showed you all kinds of examples, and it's all nice and good, but how should it really be? Let's take a look. Here is our zoo of references. So we have references that are immutable and that are references that are mutable. And the ones are constant, the other ones are nothing. And then you have lifetime. You have short lifetime, rvalues, and long lifetime, lvalues. In C++, if you look at how things bind, there's an extra feature from the rvalue reference that you can scavenge from it, that you can steal resources, which is also not a property that you want to that should appear out of thin air, right? And this is the current C++ reference binding. This is how it works. So everything binds to a constant L value. Only L values, mutable L values bind to mutable L values, similar to with R value, mutable R values. And the constant reference, the constant R value reference, you can bind a regular R value reference to. So these are the arrows you're getting. And you can see that some of these arrows go from short lifetime to long lifetime. And this is exactly the problem. This is basically overpromise, underdeliver. You are claiming that you have a long lifetime, but you really only have a short one. And that is the problem here. So how can we fix this? Well, pretty clear from the image. We would just have to turn around some arrows. So when you are binding to a reference, then you can only do this if the promise doesn't get any stronger. So if you have less lifetime, if you have less mutability, less scavengeability, then you can bind, then it's safe. So that basically means only L values should bind to constant reference, but constant R value reference, you can bind anything to, because it doesn't promise anything. It doesn't promise scavengeability. It doesn't promise a long lifetime. It's just as stupid as you could be. It's short, it's immutable, nothing else. Okay, everything should bind to constant R value reference. And now everything binds to constant L value reference. It's so sad. It's so terrible. We really shot a big hole, and now we fell into it. And yeah, what are we going to do? So sad. We try our best, okay? Is there any chance to fix it? And all these are just ideas, and they have not been implemented. And before we would have to do anything about the standard, we would first have to implement them and show them that they will work on a large code base. But anyway, so what are the requirements that we have? We know that existing code must continue to work, and even existing libraries have to work with the new code. So if we want to have these new binding rules that I just described, then we have to be able to mix these binding rules with the new binding rules with old binding rules in the same code base. So any reference uses either the new rules or the old rules. And the good thing is that these references, they are only binding. You can't change the binding of a reference. It only binds at the beginning of the reference lifetime. And after you bound to it, then that's it. It's done. So the type is basically, once the reference is there, you can use it as you did before. There's no change. Only the binding or the initial binding of a reference, that's where the change is happening. So I would suggest pragma to the rescue. There is some way to turn new binding behavior on and off, so you can mix old code with new code. And so if you declare things outside of this new binding block, you've got the older behavior. And if you switch on the new reference binding, you get the new behavior. And you can also switch it back off. Now, where do these declarations, our reference declarations, where are they happening? Well, we have some local and global variables. We have structured binding, where it would matter where it is, inside the block, outside the block. We have function and lambda parameter lists. We have member initializations in PODs, so you do them in a curly braces list, or you do initialize members in constructors. And finally, you have Lambda captures. That's all the things I could come up with where you actually initialize references. Now, all the declarations inside this new reference binding on block would bind it according to the new rules. So this is how it would look like. You have a function that's declared outside A, then inside B and C with lvalue and rvalue reference, and a B again outside. Well, this would actually be the definition of B, and here the compiler should probably issue a warning or an error, because you are using, for the declaration, you are using one kind of binding, and then inside for the definition you use another kind of binding. So maybe the compiler should issue an error. Now the effect would be that if you call, for example, here B of 5, and 5 is taking in const A, then this wouldn't compile, because the 5 here doesn't have long lifetime. It's an R value. Now the C would compile just fine, because here it's declared as in const ref. And if you call the C again with a regular A, so that's an L value, it would also compile, because everything now binds to const R value references. Now, what else would we need if you do this in the standard? So probably we need a feature test macro, whether this new reference binding is actually enabled. There may be code that should run in or outside of such a block. Functions can be implemented equivalently relatively easily. So I mean, you can probably do a search and replace all the constant reference parameters in your function with constant R value reference. And then most of the stuff would probably work. I looked through the type traits, which ones are affected. Well, the std common reference surely is, but none of the others are. So I couldn't find any other type traits that would depend on that particular binding behavior. Now, of course, as I said, I haven't tried this out, and I will probably have to hack Clang majorly to try it out and run it on a large code base to prove that it's actually working. So until we actually change the standard, which may never happen, we have to get by with some mitigations. I already showed you the Auto-cref. That is very useful to get rid of the temporary lifetime extension. For the member accessor problem, which is one of the places that's most affected, you could get into the habit to always delete the R value versions of your accessors. And we've actually done that again with a macro, so that you don't inadvertently turn an R value into an L value. The common reference can be rewritten. Here it's basically, if you look here at the implementation, it's basically the old common reference. And if this common reference finds out, oops, I returned, if you got returned an L value reference from that common reference, but any of your input is an R value reference, then you know that you are in trouble, and then you better turn your L value reference from that you got into an R value reference in the result. And then otherwise you can just use the old result as it is. Okay, now we already looked at this particular example with where you have an R value and a ternary operator between an R value reference and an L value reference, and we got a copy here. Now, if we now use the mitigation tools with the common reference that we wrote, we can actually fix this. We can define this macro that essentially is a ternary operator, but it turns its parameters or its arguments into the common reference of the two, and thereby it will actually fix the problem. So now, when you say, "Oh, it's conditional of the right and the R value reference and the L value reference," then you actually get back arguably a correct R value reference. and you don't get any immediate copy. Okay, here's the summary. It's a shame that const lvalue references are binding to rvalues. It probably should never have happened. Fixing C++ is difficult, and we would have to demonstrate it with a client implementation and a large code base. And until then, I showed you some mitigations. Thank you very much. And yes, and we're always hiring at ThinkCell. Thanks. Any questions? Would a std move trigger reference collapsing rules, fixing the issue? Yes. Yes, probably. If you write std move around the L, then the L would turn into an rvalue reference, and effectively you would fall back into the second bullet point where you have two rvalue references. So probably yes, it would fix the problem. It wouldn't trigger an actual move because you cannot move out of const, but the std move would. You essentially wouldn't have an lvalue reference and an rvalue reference in that case. I mean, you will probably. In a situation like this, where this is actually a problem, you typically probably don't want to care about the individual types. So no, it would actually be rvalue. Well, if you put the move around the L, you would get a constant rvalue reference, which would be arguably the correct result. And then, of course, you would, if you want to work on this further, you would then have to use Auto-cref to make sure that your constant rvalue reference will actually be turned into a value. So the assumption here is always that you want to do the turning into a value you want to do at the very end, when you're sure that now we need a bit of more extended lifetime, then you want to do the conversion into a value. Okay, I will be hanging out in Discord for a bit longer. So if you have any more questions, you can ask them there. And otherwise, thank you very much for joining. And yeah, have a great rest of the conference. Bye.